12.1 is the three-dimensional coordinate system. Okay, three-dimensional coordinate system. Okay, so the way we set up a three-dimensional coordinate system, okay, there are two different ways to set it up. Okay, the way that we're going to set it up in this class looks like this. Well, yeah, the way that we're going to set it up in this class looks like this. Okay, think of this like the corner of a wall. Okay, corner of the walls and the floor that are in your house. I don't want to do that, actually. Get rid of this. I'm going to make it in different colors. Let's just spice it up with some colors. This wall, and maybe this wall here. Okay, so think of this like three walls in your house. Okay, coming together in that bottom corner. Okay, so what's coming out at you is X, what's going to the right is Y, and what's coming up is Z. Okay, X is coming out, Y is to the right, and Z is going up. There is another way to write this coordinate system, and that is using your traditional X, Y, Cartesian coordinate system, but then having Z come out at you. Okay, Z is going to pop out at you here, right? So you'd have your traditional X, Y, Z, okay, but Z would be coming out at you here. Okay, now we're gonna use this one here in this class. This is the one that we will primarily use. Okay, this orientation. Okay, this orientation here. Okay, we're not going to necessarily use this one, okay, unless we start off by graphing something in 2 dimensions and then we have to move it to the 3rd dimension. Then we'll go to this one. But that's very rare cases. Okay. Now we have something called the right-hand rule. And it's going to take some imagination, but because I'm not teaching in a classroom, and I'm not going to draw a hand. It's just not going to happen. I'm not the artist in the family. That's my daughter. So she would be able to draw the hand. I mean, maybe I could draw a hand. I don't know. Okay, so it's just, again, it's not going to happen. Okay, so boom. Okay, and then we got some fingers here. I don't know. It's just boom, boom, and then we need the thumb. Don't forget the thumb. Okay, we need the thumb here. Okay, and then a little bit, and then boom. Okay, so do you see my hand there? Everybody good? See my hand? Okay, and so here's my hand, right? So the thumb is pointing up from my right hand. Does it make sense? We're gonna curl. We're gonna curl, and this is the curling action, which is this. Okay, the curling action is the X, okay, going into Y. You curl X into Y, X into Y. You curl X to Y, curl X to Y, and the thumb is always Z. Okay, the thumb is always Z. If you follow X to Y, the thumb is always Z. It's called the right-hand rule. Okay, make sense? Okay, right-hand rule, right here. Curl, and Z pops out. Curl X to Y, Z, positive Z will always be your thumb. Okay, again, that's a little bit easier to see in a classroom as opposed to over a screen. You see this right here? Okay, curl, right-hand rule, right-hand rule. Okay. Again, it's the right hand. It's coming out at you because we're curling there. Coming towards you. Okay. Here, if I curl this way, it's coming away from you. Okay. So, I mean, just look at your own right hand and you're good. Okay. Okay, so we have this orientation here. Okay, X, Y, Z. And so we have some planes. We have what's called the XZ plane. We have what's called the ZY plane or the YZ plane. And we have the XY plane. Okay. If I take a point out in three-dimensional space, okay, from the center here, I would have had to gone over, I would have had to gone over in the X a certain amount. I would have had to gone over in the Y a certain amount, and then I would have had to gone up a certain amount in the Z. Again, I would have had to have gone over in the X direction a certain amount. I would have had to have gone over in the Y direction a certain amount. And then I've had to have gone up in the Z direction a certain amount to get to that location. So X, Y, Z, up. Okay. So that's exactly what we use to get our location in space is X, Y, Z. Okay. So this is now a third coordinate, okay, in X, Y, Z space. Instead of having quadrants, we have something called octants because there's 8 of them now. Okay, if I look at a three-dimensional graph, there are 8 octants. Okay. Okay, 4 above the XY plane and 4 below the XY plane. Okay, 4 above and 4 below. Okay, if you, where's my Rubik's Cube? Okay, so if you look at the Rubik's Cube, those are your octants. Okay, this is a 2x2 Rubik's Cube. Okay, and those are your 8 octants. If that makes sense. Okay, 1, 2, 3, 4 on top, and 1, 2, 3, 4 on bottom. 4 on top, 4 on bottom, 8 octants. Does that make sense? Okay, good. Leave my cube there. Okay, let's talk about a projection. A projection. So we have this point here. Okay, I'm going to make it black. We have this point in three-dimensional space. Okay, let's say that it's at 1, 2, 3. Okay, or 1, 1, 3. Let's say that it's at 1, 1, 3. Okay, maybe we'll make it easier. 1, 1, 1, 2. Okay, so say that it's at 1, 1, 2, right? Well, what's the projection of this point onto the XZ plane, or sorry, the YZ plane? What's the projection of this point? If I were to project this point, if I were to put a light parallel to the YZ plane, where would that point be projected? On the YZ plane. Well, wouldn't it be projected at 0, 1, 2? Isn't this the projection This is the projection of the point 1, 1, 2 onto the YZ plane. Okay. Okay, what about the XY plane? Where would this point be projected on the XY plane? If I wanted to project this thing onto the XY plane, well, wouldn't it just be at 1, 1, 2? Or is that 1, 1, 1, 0? What about onto the XY plane? The XY plane, this would be 1, 1, 0. Okay, onto the YZ plane, it would be 0, 1, 2. And onto the XZ plane, okay, which is this guy over here, where would that guy be? Well, that would be at 1, 0, 2. Okay, make sense? Enough about that. If I go too fast, please let me know so I can slow down. Okay, number 1. Okay, what surfaces in the real number system cubed, that's R3, we just call that R3. It's the real number system cubed. This is 3 space. Okay, 3 space. This is your, okay, this is your 3-dimensional Cartesian coordinate system, which we just call 3 space. Okay, what surfaces in R3 are represented by Z equals 3 and Y equals 5. Okay, so which ones are represented by Z equals 3 and Y equals 5? Well, let's look at Z equals 3 first. Okay, where would Z equals 3 be located? Where would just a Z value of 3 be located? Well, it'll be located up 3. So if I had the point 0, 0, 3, that should be located on Z equals 3. Does that make sense? Because what is located at Z equals 3? Every point that has a Z value of 3. Every point that has a Z value of 3, well, wouldn't that just be a plane? A sheet that runs through, okay, that runs through 3. Wouldn't that just be a sheet that runs through 3? Does that make sense? This is Z equals 3. It doesn't matter where I'm at on this plane, the Z value is always 3. It's just a parallel, it's a plane through Z equals 3 that is parallel to, or I could say the plane through 0, 0, 3, parallel to the XY plane. Okay, it's parallel to the XY plane. Okay, why? Because there's X, here's Y, and here's Z. Okay. Okay, what about Y equals 5? Well, very similarly, we're going to go out in the Y direction 5, 1, 2, 3, 4, 5, and we're going to have a plane, okay, that slices through Y equals 5. Okay, so we've got this point here on the plane. Okay, this point here is on that plane. We've got this point here on this plane, and that goes through Y equals 5. Okay, that is a plane parallel to which? Well, it's the XZ plane, right? parallel to the XZ plane. Oh, okay. Well, that's cool. Okay, again, if you have any questions or you think my drawings suck, feel free to let me know, because they do suck sometimes. And you know, this is a different medium than I'm used to working on. So hopefully this makes sense. Okay, there's my plane. Okay, like a sheet of paper, right? This one's vertical, the other one was horizontal. Z equals with a horizontal plane, Y equals is a vertical plane. X equals would be a vertical plane as well, just in a different orientation, 90 degrees from the X. Right? So X, Y, Z. Okay, number 2. Which points X, Y, Z satisfy the equations x squared plus y squared is less than or equal to 1 and z equals 3? Which points satisfy this? Okay, well, let's think about this for a second. We already know what z equals 3 looks like, right? That's just that's that plane we talked about. 1, 2, 3. Okay, that's that plane that goes through 3 here. Okay. Okay, so we've got 1 here. We've got 1 here. Got 1 here. Okay, I'm going to go 1 in the opposite direction here. 1 there. Okay, so if we look at x squared plus y squared equals 1, x squared plus y squared equals 1, what is that the equation of? What is that the equation of?
A circle.
Circle, very good. Thank you, Michelle. Okay, it is a circle. Okay, so it's a circle of radius what?
1.
Yes, it's a circle of radius 1. Okay, and it's at the origin, and this would be on the xy plane, right? Okay, so let's draw that circle. There's that circle on the xy plane. Okay, but what do we know about the z value? What do we know about the z value from here? The z value has to be at 3, right? So can it be at 0? Can the z value be 0? No. Okay, it can't be at 0. It's got to be at 3. So what I'm going to do is I'm going to bring these lines up here. Okay, and then I'm going to draw that ellipse again. Okay, and you can see that this is going to be the top of a cylinder. Okay, this is the top of a cylinder. Now, is it just the ring though? Or is it the surface inside the cylinder? Is it the top of the can? Is it just the ring around the can or the circumference? Or is it the surface area of the top of the can of soup here? Well, because we have this less than or equal to, it's everything inside. It's everything inside here, right? So isn't that a circle of radius 1 centered or risen to the z equals 3 plane? Does that make sense? So I don't know how we want to formalize this. Maybe the blue will be, or the purple will be formal one here. Okay, so let's formalize this guy and just say, look, this guy is the surface that I'm looking for. Does that make sense? That's the surface that I'm looking for. Okay, it's the top. It's the top of a cylinder with radius 1 and bounded by z equals 3. Okay. Now, I didn't have to stop here either, just to let you know that this cylinder goes down forever and it goes up forever. This cylinder goes up and down infinitely forever. Why? Because z could be anything I wanted it to. If I was just looking at this is the equation of a cylinder. Okay, this is a cylinder in 3 space. Okay, if I saw this in 2 space, in R2, okay, not to be confused with R2D2, because that's a whole other conversation. Okay, but if we were in R2 here, it would just look like this, right? X, Y, right? And then it would be what? This would just be a disk of radius 1. This would be a disk of radius 1. Why do I say disk? Because it's the whole thing. Okay, it's a disk of radius 1. That's what x squared plus y squared is less than or equal to 1. That would be a disk of radius 1. But what happens as soon as I move from R2 now to R3, what happens? Well, I end up with a third dimension. And so this cylinder becomes a rod, or this circle, sorry, becomes a rod or a cylinder that goes in infinite direction. Okay. Okay, make sense? That make sense? You can fill those in if you wanted to. Doesn't matter. Those are slices. We call those traces. Okay, they're slices of the cylinder. Slices. Okay, maybe this is a slice at z equals 3. Maybe this is a slice at z equals -2. This is a slice at z equals 0. We add a third dimension and we just end up stretching. Okay, it's the exact same thing that you already know how to do. Why? Because let's look at a number line. Let's look at what happens when we do x equals 1, right? When x equals 1, what is that? What is x equals 1 on a number line? Where is that located? Well, here's 0, right? Where's x equals 1 going to be located? 1 unit. 1 unit where?
To the right.
To the right. There you go. Okay, so we'll do 1 unit to the right, okay? That make sense? 1 unit to the right. So I'm gonna put a point here because in 1 dimension, in just R, okay, in the real number line, R, oh geez, I can't write. Okay, R, okay, in R, this x equals 1 is a point. What about R2? What is this x equals 1 become? In R2, what does this x equals 1 become? Let's add a second dimension here.
A vertical line.
Yeah, it becomes a line, right? It gets extended as a vertical line, x equals 1, now it's a line. And then what about R3? Now what happens?
Plate.
Yeah, it gets extended again, right? So this was x, this was y, that means z's coming out at me. And so it becomes a plane, right? Does that make sense? So now R3, it's a plane. Right? Okay, cool, very cool. Okay, this drawing is not so good. This looks like a ball of tennis balls. Tennis balls? No, it's not tennis balls. Okay, it looks like a carton of tennis balls. They're slices. They're slices. They're not balls. Okay, they're discs. These are discs. Okay, they're discs. Okay, let's move out of that, for example. I don't know. Do you want to do one last one of these before we move on? I don't know. Ah, sure. Let's just do it for kicks and giggles. What time we got? 4:46. Time we over? Oh, we're over in an hour. 5:40, right? 5:45. Okay, good. Yeah, whatever. I'm not gonna do that. Okay, let's just look at the distance formula real quick. Okay. Okay. So this guy, I found this kind of funny. I don't know if you've seen this t-shirt. I'm thinking about ordering it. Okay, social math. Come on. So social distance, I don't know. There's a lot of them out there. Social distancing, so you see social and then the distance. Okay, social distance. Social distance. It's kind of funny. I don't know. They had a better one. Okay, social distance. Oh, here it is. Math teacher quarantined, social distance. So social distance, anyway. You get the idea. Okay. I thought they sent me one. They're like, oh. Okay, so they have this thing, and then they're like social distance with the distance formula. Anyway, whatever. Okay, let's do the distance formula in R3. Okay, the distance formula R3. The distance between, okay, P1, P1, 0.1 and P2, maybe I'll go P1, okay, is X1, Y1, Z1. Okay, and P2, X2, Y2, Z2, the distance between 2 points in 3 space. Okay, maybe from point here to point here, and then we want to find the distance through 3 space, right? Through 3 space, we would have to go right over an amount, and then up an amount. I don't know how you think about that, but something like this. Should be over a little bit, like this. All the lines should be parallel. Okay, so, right? So we'd have to move distance in 3 directions. It would be the difference of the x's, the difference of the y's, and the difference of the z's. It's almost like the Pythagorean theorem in 3 space, right? So we'd have the distance, the difference in the x's. This would be delta x, this would be delta y, and this would be delta z. Okay, change in y, change in x, change in z. Okay. I mean, if you want me to start with x, I can. It doesn't really matter. I can start with x. I could go x first, and then y, and then z, right? So maybe I'll do that just to keep it the same. Okay, so this is delta x. this is delta y, and then that's delta z, right? So this would be the change in x. This would be the change in, I'll put those in a different color, because the black is just getting all over the place. The change in y, and then the change in z, right? So that's the distance between those two, delta x, delta y, delta z, right? So how will we do this in two space? In two space, we would use the Pythagorean theorem. Well, we say that the distance between P1 and P2, this is not the absolute value of the product, this just is the distance between P1 and P2, absolute value is distance, okay? Just think about that weirdly for a second. Okay, the absolute value is distance, and the distance in R3 is the same thing as R2, but, okay, it's going to be x2 minus x1 squared plus y2 minus y1 squared plus plus z2 minus z1 squared. Okay, that's the distance from them. Okay, let's look at the equation of a sphere. Okay, what's the equation of the sphere? So a sphere, okay, is equidistant, right? It's equidistant from some point, right? Equation of a sphere, equidistant from some point. Okay, so maybe we have this point out in space here. Get rid of that point. Okay, say we have some point out here in space, and we want all the points that are equidistant from this point in 3 space, all the points that are equidistant from this point, okay, in 3 space, right? So what would you call the distance from the point to the sphere? Okay, the distance from the point to the sphere is a radius, sphere of radius r. And we would always want r to be constant, right? We would want r to be equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And we're just going to square both sides, and it's going to give me r squared. Okay. So now I'm gonna let x vary. I'm going to let x, y, and z vary. That would just be from one point to the other, but I want a locus of points. So this is going to be x, y, z. Okay, so this is the locus of points. We say this is the locus of points, locus of points. Equidistant, from point x1, y1, z1, okay, from x1, y1, z1. Okay, why am I calling this point C? Why, I can't write 1 today, what the heck? Z1, okay, why am I labeling that point C? Why is that point C there? Anybody know? Why is that there? It's constant? No, it's not constant.
It's the center.
It's the center, exactly. Thank you, Omar. It's the center of the sphere. That's why it's point C. Okay, it's the center of the sphere. Handwriting is so bad today. Okay, so x1, y1, z1 is the center of the sphere. It's from the center, okay, with distance r, right? So there you go. There's your equation of a sphere. In R3. Okay. Okay. Let's do an example. Did we already do an example? I don't know. I don't think so. Nope. Okay, let's do example 1 here. Okay. Show that x squared y squared z squared plus 4x minus 6y plus 2z plus 6 equals 0 is the equation of a sphere, and find its radius. Okay, so I want to take this guy and turn him into something that looks like this: x minus x1, y minus y1, z minus z1 equals r squared. I want to turn this big equation up top here into something that looks like this. What are we going to have to do? What's the tool that we're going to use in order to get this to look like a sphere? What do we call the operation that's going to help us get a binomial squared?
Completing the square?
Yeah, completing the square. Thank you. Okay, absolutely. So I'm gonna group these: x squared plus 4x plus y squared. I'm gonna actually save a space here. Okay, plus y squared minus 6y plus z squared. Okay, plus 2z plus, I'm going to save a space, and then I'm going to put that 6 on the other side. Okay. Okay. So let's take half of 4. What's half of 4? It's 2, and then let's square that. That's going to be 4. Let's take half of 3 or half of 6, square it. That's 3. Half of 3 is 3. Half of 6 is 3. 3 squared is 9. So we're going to get a 9 there. And then half of 2 is 1. 1 squared is 1. So we're going to do 1. 1 plus 9 plus 4, that's 14. So we would have added 14 to one side and 14 to the other. Okay. And so now we can factor these.
I think you forget r squared, right? On the right.
No, I haven't forgotten r squared. Okay. This is going to be x plus 2 squared plus y minus 3 squared plus z plus 1 squared is equal to 8. Okay. Or the way I could write this is radical 8 squared, which is 2 radical 2 squared. So I didn't forget r squared at all. This is a circle with center -2, 3, -1, with radius 2 radical 2. That's it. Boom. There's your radius. Does that make sense? Okay, number 2. What is the region in R3 represented by the equations one is less than or equal to x squared plus y squared plus z squared is less than or equal to 4, and z is less than or equal to 0. So what's the region that is represented by these equations? Well, this one is equation of a couple of spheres. Okay, it's actually a sphere centered at the center, right? So maybe I'll use black on this one. Okay, that's a sphere centered at the origin. Okay, centered at the origin. And what about it? Well, it starts, it's the volume between a sphere of radius 1 right? So it's the volume of a sphere of radius 1. Okay, so maybe this is the sphere of radius 1 here. Right? But then we also have another sphere of radius 4. Oh, okay. Right? So we have a bigger sphere. Let me put that one in purple. Okay. We've got this one now too. I don't know. It's not going to be to scale. Oh, whoops. This is too. I know it's not going to be to scale because I'm screwing it up already. There we go. Needs to be. No, that was right. Needs to be like this. Yeah. Hey, can you hear me now? Whoa.
Oh, it's kind of echo.
That was not good. Can you hear me now?
Yes.
Yeah. For whatever reason, Zoom cuts out periodically. So we want below the z equals 0 plane. So it's between these two. Okay, it's between these two, but below the z equals 0 plane. Okay. So what I'm going to do is I'm going to kind of chop this guy off. Okay. Chop you off, sir. And just have below. Okay. So think of this like a cantaloupe, right? Has anybody ever eaten cantaloupe? Right? So you have all the seeds in the middle here, right? You have all the seeds in the middle. And then you have the cantaloupe. You cut that cantaloupe in half, you have all the meat of the cantaloupe in half. And so that's exactly what you get. Okay. So it's this volume. It's the volume between r equals 1 and r equals 2. Sorry, it should be 2. R equals 1 and r equals 2. Okay, between r equals 1 and r equals 2. Okay, and then it's everything in between. Okay, let's talk about vectors. Okay, 12.2. Okay, 12.2 vectors.
Sorry, Professor, can you scroll up? Thank you.
Sure. Okay, so for a vector, there's an initial point and a terminal point. Okay, so initial point and terminal point. Okay, initial point and a terminal point. Okay, we'll call the initial point A, the terminal point B. Okay, let's do some vector addition. Okay. So this is the triangle law. This is too thick. Let's go back. Triangle law. Okay, the triangle law says that we put vector AB plus vector CD, or sorry, BC. So vector AB plus vector BC is equal to vector AC. Okay, vector AB plus vector BC is equal to vector AC there. Okay, so BC, I'm going to make this a little slantier. Okay, BC is what? This is called the head to tail law. Head to tail. Okay, head to tail. So this is A, B, and so what would be my resultant vector? It would be, oops, not that. It would be right here. That would be my resultant vector. Okay, that's the distance. Okay, that's the vector addition. Okay, so this is AC. Okay, that's the triangle law. Then there's the parallelogram law. Okay, and the parallelogram law states, okay, that if I have AB plus AD, well, let's draw the picture first. We have A, we have D, we have B. let's do this. This is A. Nope. Let's just keep it like this. Okay, this is A. Okay, so we're going to go A, B, let's get rid of that. Okay, this is kind of hard to draw this, but I'm just trying to draw a parallelogram. Okay, so this is C, right? Okay. So what is AB here plus AC is what? Is equal to AD. Okay, AB plus AC is equal to AD. And where's D? C. And D ends up being this one here. Okay, so this is D. Okay, does that make sense? That's called the parallelogram law. You just, okay, and this is tail to tail. Okay, that's tail to tail. If you've got two vectors tail to tail, you draw a parallelogram. If you've got two vectors head to tail, then you just draw a triangle. Okay, either way. Okay, because say that I looked at the triangle law here, but I wanted to move it from head to tail to tail to tail. Well, wouldn't I just be drawing a parallelogram? Say I move this guy, BC, to now over here, C, right? So to AC. Right? Say that you push this, I don't want to get it too cluttered. Get rid of my AC here. But say I push this guy over here, right? And instead of head to tail, I went to tail to tail. Well, wouldn't that just going to tail mean that I would be going, okay, doing the same thing? This would be D, by the way, not C. Does that make sense? Okay, so hopefully. Okay. Let's talk about scalar multiplication. Okay. Okay. So scalar multiplication. If C is a scalar and V is a vector, I don't know why someone has their mic on. I want to mute everybody. If C is a scalar and V is a vector, then the scalar multiple CV is the vector whose length is the absolute value of C times the length of v, okay, and whose direction is the same as v. Okay. Okay, direction the same as v. Okay, if c is greater than 0 and opposite, if it's positive, then it's just going to be in the direction of v, and opposite to v if c is less than 0. So it's going to go in the opposite direction. Just like what you did with, polar coordinates. Okay, if you had a polar coordinate and you had r be negative, it went in the opposite direction, right? Remember that? Your polar coordinates. Right, so if you had, if you were out here at and r was equal to -3, then what would happen? In your polar coordinates, you would actually end up positive, right? So if you said that you were at r theta of r is -3 and theta is pi, right? Where is that point located? Right? Well, you go 180 degrees over here, right? And it's 3 units out, right? And 180 degrees, but then what do? You point it in the opposite direction. It's the same thing with a negative times a scalar. It's polar coordinates are like scalars. Are like vectors. They behave like vectors. Okay, we're actually going to be doing a lot with polar coordinates. Okay. Okay, the difference between two vectors, u minus v, can be thought of as u plus -1 times v, right? U plus -1 times v, or u plus -v. It's just going to go in the opposite direction, right? We have vector u and vector v, okay? We have vector u, vector v, but if we want the difference, right? If we want the difference, then it would just be u minus v. Okay, so let's think about this for a second. If I have vector v here, and I have vector u here, then how would I get u minus v? How would I get u minus v? Well, I can't go positive v. I would have to, okay, let's think about this for a second. Okay, I want u minus v, right? So u minus v. So I want to find the how to add u plus v. Well, how do I get u plus v? Well, u plus v, this is tail to tail, so wouldn't it just be the parallelogram law? Right, for u plus v, that one's easy. But how would we do u minus v? right? How would we do u minus v? Well, we would have to go in the opposite direction, right? We'd have to go in the opposite direction as a v. So this is minus v. Oh, okay. And so it'd really be just u plus a negative v. Let me make this go farther. Okay. And so when I add, now when I do the parallelogram law, it goes down instead of up. Make sense? So this guy here is u minus v. Oh, it goes down instead of in between. Okay, that's u minus v. Okay, the other way that we can think about this, okay, maybe a better way to think about this is let's actually do u plus v here. Let's look at u plus v and let's see what happens. Well, let's keep the same graph. I'm just going to move u minus v. I'm going to move the location of u minus v, okay? So let's move this guy. I'm going to move the location of u minus v. So this is still u minus v. Would you agree? This is still, that's still u minus v, right? Does that make sense? Isn't that's still u minus v? It's just, I just moved it. I translated it from the tail of v and u to the head of v. I'm sorry, and right, the other way around. From that, I translated. Pedro, turn off your mic.
Yes, I'm sorry, my microphone wasn't working. I just fixed it up.
Okay, turn off.
I saw that you put me attendance out. Could you put me attendance on?
Can we talk about this after class?
Okay, sure.
Thank you.
Thank you.
Mic off.
Okay, I'm listening all the time.
Sounds great. Or not. I'll turn your mic off for you if you really need me to. Okay. So u minus v, I'm going to translate this up. Okay, translate it up. And so what I'm doing here, okay, let me just kind of get rid of the colors, is the big point here is this, okay? Here's v, here's u. What's u plus v? U plus v, let's draw a parallelogram. Okay, what's u plus v? Well, it's the diagonal here of the parallelogram, right? Isn't this u plus v? That guy is u plus v. And what was u minus v? U minus v. Isn't that the other diagonal? Isn't that the other diagonal here? Isn't that u minus v? Oh, that's it. So one diagonal is u plus v. The other diagonal is u minus v. That's the point there. Okay, representing a vector from 2 points. Okay, given A, x1, y1, z1, and B, x2, y2, z2. Okay, vector A is, okay, just the difference between the x components the y components and the z components. Okay, that's the vector A. Okay, let's talk about the magnitude of a vector. Okay, so again, a real quick one on this one. Say we had 1, 1, 2. That's a vector, or that's a point. Okay, and we'll call this point P, and then we have point Q, right, at say 2, 3, 4. How would I find the vector? It's just going to be the difference between these. Okay, and so, gosh, I don't know how much into this I want to get on the first day, but you know, we could say that vector PQ is equal to 2 minus 1, which is 1, 3 minus 1, which is 2, and 4 minus 2, which is 2. Okay, that's the vector. And again, this comes to us from these graphs. Okay, so if I were to graph these points in space, so say that's the first point and the second point, right? So, and then we have the origin. How do I want to do this? This point, we'll call this point P, we'll call this point Q, and we'll call this point O for the origin. Okay. And so how do I want to find the vector P to Q, the vector P to Q? Okay, the vector P to Q here. Well, we take the vector 0P, OP, and we take the vector OQ, okay, OP, OQ, right? Okay, take those two vectors. What are we going to do? We're going to subtract them, right? Okay. So this is going to be vector OQ minus OP gives me vector PQ. Okay, OQ minus, okay, OP gives me vector PQ. And since the origin is 0, 0, 0, everything works out. Okay, because we just end up with vector Q, okay, which is vector Q. What is vector Q? Well, vector Q starts at the origin, right? So if we say vector Q is the origin, well, where is it going to end up? Well, it's just going to end up at 2, 3, 4, right? And then what's vector P? Well, that's the origin, which is just, I'm just going to subtract zeros from that. And so where's that going to end up? That's going to just be vector 1, 1, 2. And so what happens when I subtract those two vectors? That gives me vector PQ. Okay, when I do Q minus P, that gives me PQ, vector PQ. Okay. Let's talk about the magnitude of a vector. Okay, in 2 dimensions, okay, the magnitude of vector in 2 dimensions in R2, okay, if I have is just going to be the distance from one vector to the other. Okay, so this is A1, vector A1 squared plus vector A2 squared. Those, if I have the different components here, if A is equal to A1, A2, okay, I could do X1, you know, X1, Y1 if you really wanted to. Maybe I'll do that just to make it easier. Okay, so that's my X1 component, and this is my Y1 component. Okay, and so what would this be? This would end up being, okay, X1 squared, Y1 squared. Okay, but these are components to my vectors, to my vector. Okay, okay, so in R3, Okay, this is going to be x1 squared plus y1 squared plus z1 squared. Okay, it's just the distance formula in 3 dimensions. Now, why do we not have why is it just x1? Where did the other x go? Well, it's because we're starting this vector is being measured from the origin. It's measured from the origin. And since it's measured from the origin, the distance and the vector are the same value. Okay, and if I were to look at the distance formula, right, the distance formula in 3 space, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Well, what's x1, what's x2, y2, z2? Well, x2, y2, z2 are all 0. All 0, right? Because isn't that the origin? 0, 0, 0. So what happens when I plug those in? Well, don't I just get x1 squared, y1 squared, z1 squared? That's the magnitude. So basically it's saying, look, I have vector A here, I have vector A starting from the origin. Let me do a different color. Okay, I have vector A starting from the origin and going out. Okay, and what's the magnitude of that vector? Well, it is just the location of that vector, right? So what's the magnitude? Well, it's just the location. It's the distance. Okay, it's the distance from the origin. Okay, that's the magnitude. So I hope that kind of made sense. So let's say that this is out at I don't know. Let's say that it's out at 1, 2, 3, right? Okay, what would be the magnitude of this vector that's out at 1, 2, 3? Well, the vector itself would be vector 1, 2, 3. So we'll just call this V for vector. Okay, that vector is equal to 1, 2, 3. So what would be the magnitude of that? What would be the magnitude of vector V, or absolute value V? It's really magnitude. Okay, but they're synonymous, absolute value and magnitude. This would be the square root of 1 squared plus 2 squared plus 3 squared, which is going to be the square root of, what is that, 14? Okay. So that's the magnitude of this vector. Okay. Okay, let's talk about the standard basis vectors. We'll finish up here. The standard basis vectors. Okay, they're called I, J, and K. Okay, called I, J, and K. Have length of 1 unit. Okay, and point in the direction of the axes. The axes, X, Y, and Z. And Z. Okay, so how does this work? Well, there's just like, think of the unit circle, but these are the unit axes. So I, okay, I is here. If this was out 1 unit, this would be I. Okay, I is 1 unit in the direction of X. That's I. Okay, where's J? Well, this is J. 1 unit, okay, in the direction of Y. That's J. And then where's K? Okay, K is 1 unit up. That's K. Okay, they're each 1 unit in length. And they're called the standard basis vectors. Because we can multiply any of these standard basis vectors by a vector, and it gives me that vector in the direction, okay, of these guys. Okay, so think of K as, so think of I as 1, 0, 0. Think of J as 0, 0, or sorry, 0, 1, 0. And think of K as 0, 0, 1. Okay. Okay. So I can rewrite any vector in terms of the standard basis vectors. So if A is equal to A1, A2, A3, okay, then A is equal to A1I plus A2J plus A3K. Now, why is that? Because I'm going to get the exact same result if I do this addition of these vectors. Okay, now why is that? Okay, so if I let let's let A1 times I, right? A1 times I. Well, what is A1? That's just the component of my original vector. A1 times I is 1, 0, 0. So what do I end up with? I end up with just A1, comma, 0, comma, 0. Right? This makes everything else zeros. And then what if I let A2 times 0, 1, 0? Wasn't that just 0, A2, 0? And then if I do A3 times 0, 0, 1, isn't that just 0, 0, A3? And now let's add those three vectors together. Now, in order to add vectors, we have to add component by component. Okay, so addition of vectors, vector addition, is component by component. Okay, and so we're going to add all the first values together. Well, what's A1 plus 0 plus 0? Well, that's A1, which is a very tasty steak sauce. Okay, what's 0 plus A2 plus 0? Well, that's A2. And what's 0 plus 0 plus A3? So that's A3. And what this allows me to do is it allows me to write vectors in this form. This is called the standard basis form.
To allow web search content,
No,
you'll need to change.
Stop. Go away, Siri. I said standard basis, not theory. Okay, standard basis form. Okay. She always comes on when I teach pre-cal and stuff, because whenever I say series and Calc 2, whenever I teach Calc 2, I say series, and she always wants to butt in to my lecture. I'm like, go away, Siri. I did not call you. Because she thinks that A series is Hey Siri. A series is not Hey Siri. So that's not the way it works. Okay? All good in the head. Okay, let's do one final example here. Okay. Number 3. I think that's number 3. Maybe there's just number 1. Who knows? I don't know. I lost count somewhere. Let's do one final example. Okay, find the tension T1 and T2. The tension, say in T1 and T2. Okay, so got this bad boy here. Okay, we've got this setup. Because I think you have one like this in the homework, so I want to make sure you can do this. Okay. Okay, this is for all my engineering majors. Okay, so 100 pounds is being suspended. Okay, this is our physics problem for the day. Okay, and so I have T3 here. I have T2, and I have T1. This is a 50-degree angle, and this is a 32-degree angle, even though it doesn't look like it. Okay, so how am I going to find the tension in T1 and T2? Well, because this is in homeostasis, what do I know about the tension on all 3 of these? They have to be equal, right? Doesn't T1 plus T2 have to equal T3? Isn't that true? Okay, so I'm gonna say that, okay, T1 is equal to, okay, and you can verify this if you want by drawing some rectangles here. Okay, because if that's 50, then this is 50. If that's 32, then this is 32. Okay, but I'm going to say that T1 is negative cosine 50 degrees. Okay, T1I plus sine of 50 degrees T1J. What we're doing is we're saying, let's make an X component and a Y component out of T1. Let's make an X component and a Y component, because this is being pulled in this direction, okay, my X component, and it's being pulled in this direction, my Y component. I'm going to do an X component and a Y component. You can use some trigonometry to figure out those tensions. Okay, same thing with T2. Same thing. This is negative cosine of 32, T2I in the I direction, which is the X direction, plus, okay, the sine of 32 degrees T2J. Okay. And so now what do I know? Well, I know that if I add these two, okay, I should, come out with the tension on T3. Well, we'll get to that in a minute. Okay, so notice that, though, that the X for T1 and the X for T2, right? The X for T1 and the X for T2 have to be, okay, equal to each other. Okay, the T1 X direction and the T, because it's not moving in either direction, in the X direction. Those X directions, what's going on in this direction has to be equal to what's going on in that direction, because it's in equilibrium, right? So I know that T1 sub X is equal to T2 sub X. Oh, okay. So that tells me that negative cosine 50 degrees, T1, okay, is equal to negative cosine 32. If I were to add these together, they'd have to add up to 0. Okay. they're just going to be equal to each other. Okay. So negative cosine of 32 degrees, okay, T2, okay, and so those have to be equal to each other. Okay. The other thing that I know is that the Y value and the 100 pounds has to be in equilibrium. See, this is going to be, there's going to be a Y value over here. We'll call this Y1. And there's going to be a Y value over here. We'll call that Y2. And I'm sorry I'm a minute over, but I want to at least get the setup here for you. Okay, this is, so now I know that, let's just go T1 here. Let's divide by the negative cosine 50. Okay, negative cosine of 50 degrees. And so you're going to see that we can set this up to be a system of equations. This is cosine 32 over cosine 50. Okay, right? Okay, and so that's my first equation. My second equation would be the sines. That T1 plus T2 has to be equal to 100. So T1 plus T2 has to be equal to 100. Okay, well, this is in the y directions. So that was the sine of 50 T1 plus the sine of 32 T2 has to be equal to 100. So I can solve this. I can solve this for T1. Okay. Or I could just sub in. Can't I just sub in and then I could solve? Couldn't I just sub that in for T1 and then solve for T2? It's exactly what we do. And we come out with T2 is approximately 64.91 pounds. And then we sub back in and we get T1 is approximately 85.64 pounds. Okay. Okay, and that's all.